Good morning. Welcome to Krishna's class. Last time we were discussing the Lebesgue-Radon theorem, and we gave a outline of the proof in the sense that what are the major steps of the proof, and had some discussion on that. Now in this talk we give the elaborate, that means substantiating each one of the statements that we presented there as steps, various significant steps in the construction of it. So let us begin with that. Before that, let me just read out let us recall the statement of the theorem. Now you see that xm is a measurable space, and mu is, now what are given is there are two measures given on the same set, namely mu, which is a positive sigma finite measure, and lambda, a complex measure. So there are two measures given on this. One is a positive sigma finite measure, and the other one is a complex measure on x. Now what this theorem explores is the relation between lambda and mu. Then you see, what this proves is that every complex measure on this space can be represented as an integral involving the given measure. Okay, and the way in which it is done is this, that the statement is that there exists a unique pair of complex measures lambda a and lambda s on M, such that lambda is the sum of lambda a plus lambda s, and lambda a is absolutely continuous with respect to mu. Lambda s and mu are actually singular. Now there exists a unique h in L1 mu such that lambda a e is the connection. Lambda a e is given by integral over e h d mu for every e in M. Now these are the two statements that goes with it. What we have is this. What we have in fact proved is that if you have a breakup like this as given in A, then it is unique. So we'll note the breakup of lambda as unique. So if you have such a breakup, that is what it is. If you have such a breakup, then that breakup is unique. Okay, or in other words, given lambda a and lambda s are uniquely determined with respect to mu only, with the property that lambda a is absolutely continuous with respect to mu, lambda s is singular with respect to mu. Now this is a unique, and this we have already. Now what is remaining to be proved is the existence. So the problem remains is existence of lambda an so this is existence part that we are doing, and it's quite a difficult task. In fact, what we prove is 2. That means given corresponding to lambda a, there corresponds then h belonging to L1 such that the relation 2 holds. Okay, so this is what we prove, and once we prove this, automatically the existence will be given, and we have already shown that if such a lambda breakup exists, then it is going to be okay. So it's a wonderful theorem. Now the task is very clear. What we want to, this is given mu lambda, there exists so you have to go from the pair lambda mu to h such that 2 holds. So this is the important. So we have to identify a function, a L1 function with respect to mu such that this result holds. So this is the important part. Okay. So how do we go to this? We have already described it. So let us work out the step one after another. So we prove that there exists, we introduce some ad hoc things. There exists a bounded measure phi on. So we have to introduce this ad hoc measure phi on x. How do we do that? Now lambda is first we assume bounded measure. So the strategy is very clear. We prove it for a positive bounded measure, and then we exploit the fact that every complex measure has a real part and imaginary part. Both are real measures, and then we can split each of these real measures to a positive measure or the difference of a positive measure or difference of 2 positive measures constructed out of it. And for each positive measure you can apply the theorem and then combine them together. Okay, right? So that is a strategy. So there is nothing really difficult about that. So let us do that. Okay, so this is our assumption. We assume lambda is a positive bounded measure. Then we can associate with mu a function w defined on x Okay. So what we have this is that, and we choose this in such a way, or we have it in such a way that 0 less than W less than. This is one of the lemmas that we have. X such that less than on X, of course. So this we have already done. You have actually constructed, given a details of the construction of such a function. Okay. Now what we do is the following. Write d phi to be equal to d lambda plus d mu w d mu with this particular choice of w. So this means the following. Now w d mu we can write as d mu prime, defining a new measure on X, and therefore then what we have is d phi equal to d lambda plus d mu prime, or you have phi equal to, therefore once you have this mu prime is determined, lambda is known, and therefore this is the definition of phi. Okay, so the consequence is this, right? We have integral over x f d phi is equal to that means f d mu prime, actually d mu prime is w d mu. Okay, and for any negative, non-negative measurable function f. for any non-negative measurable function. Now this is proved as follows. First of all, you observe that this holds for chi e, for any e. Okay, so you take f. See, the steps are for f equal to chi e. If you do that, then this is what you get. You have phi e equal to lambda e plus integral over e w du. Okay, this is what you get, right? So this is something that holds for chi e. Then what you do next? You take simple functions. Simple functions are linear combinations of these kind of the characteristic functions chi e. Okay, so from there you can go to their finite linear combination. Therefore, one can easily prove that this relation holds for all all simple functions. Simple. Then you come to the next level, namely you take a non-negative measurable function. You can approximate it through a sequence of simple functions, simple measurable functions, and then you can work with that. So you see, then you proceed to the limit as n tends to infinity. So you have relations of this kind. I just list it out. Simple functions Sn. So for a characteristic function, for characteristic functions on E, that is the first part. Secondly, the next step, true for simple functions. And then you take simple functions Sn converging to f measurable. Then what you do? You see that this relation holds integral over x Sn d phi equal to integral over x Sn d lambda integral over x Okay, now these are simple functions. Okay, let n tend to infinity. Then you can, in fact, justify this transfer of limiting process with the integral. Therefore, you get integral over. So choose Sn converging to f. Therefore, you have integral over x then use the dominated convergence. theorem. Okay. So that is this is F is any non-negative measurable so use the dominated convergence theorem. So that's the strategy. Okay. Therefore, this theorem holds for any non-negative measurable function. Now, suppose the next step is if f belongs to L2, fine, we take that such functions, then by Schwarz inequality, what we have is this. We take f this is true. This is true. And this is of course bounded by integral over x mod f d phi. You go to this relation, d phi is equal to d lambda plus d mu prime. D mu prime is a non-negative measure. Therefore, you have this inequality. Or you take one more step and write d lambda equal to d phi minus d mu prime, and then drop that second term, you will get this result. Okay, so that's it. And this we apply Cauchy-Schwarz, so you get integral over x right. So you are writing mod f as mod f into 1. So the second part is actually one d phi half. And that gives and this part will be simply phi of x. Okay. Therefore, what one gets is this is we get integral over x f d lambda is bounded by some constant k times norm of this is the L2 now. Right here. Right. Is the L2 now. This is the L2 norm. Okay, so henceforth we shall simply write norm to designate this. This for our purpose. Therefore, what do we infer? So now look at this. So you take a space L25, which is a Hilbert space, and we choose an element F belonging to that. Now you see that the map over the integral over x f d lambda is a scalar, and you can easily show that this is also linear. So this is a bounded linear transformation. Sorry, bounded linear function defines what we have proved is it is bounded. Bounded linear functional on the Hilbert space L2. Okay. So what is the implication? What is the immediate inference that you can make? Suppose you have bounded linear function on a Hilbert space. Now this can be represented through the inner product by a unique choice of a function from the class, and the representation will be given as follows. By Rees representation theorem, you have integral over x f g. Okay. So this is the inner product in L2. Okay, so this defines a linear functional, and therefore it's a bounded linear functional, and therefore you can associate it with a uniquely determined G with with this particular linear function. So what you have is this. This is you can do. This is final. So this G represents, or the other way around, phi is represented by G. G is an L2 function. Okay, so G belongs to L2. And what is this? And we have F since we are working on real functions, this is therefore we have integral x f d lambda equal to integral x f. So this is the conclusion, and this is how we have obtained a G. So we have now obtained a G. Okay. So we have come to the next level, right? So what we have is we started with mu w, then we have defined phi, then now we have come to a G associated with G lambda. These are the steps that we have gone through. Okay, so your H that is going to be finally the representing function is going to be something that is constructed out of G. So this is an intermediate. So G is an intermediate. Now we need some exploration of G. So let us explore G. What are the properties of G? This is important. In fact, what we want to prove is the following. We want to prove that 0 okay. So for that, what we do is this. We first show that this is the first thing that we prove. How do we prove that? The characteristic function of U. We take only those sets for which phi is strictly positive. So this is an important condition because it comes in the ratio in the denominator. So to substantiate that, we need this. Okay. Now we have now d phi now put that's what we do. Therefore, what will be the consequence? So you get lambda E is equal to integral over this is chi E integral over E. G is there. G d phi. Now we have d lambda equal to d5 dt. Therefore, lambda e equal to phi e minus integral over e dt. Okay, which implies lambda e is less than or equal to 5 for with phi, of course, with the condition that we have chosen is that phi e not equal to strictly greater than 0. Therefore, this implies less than or equal to 1 upon phi e over e, which is less than or equal to what you have is lambda e by phi e less than or equal to 1. So this is what we get. So we get this relation, which implies integral over so we have the following 0 less than or equal to 1 upon phi e less than or equal to 1. So what does this mean? This means, you see, you have got this lambda e is less than or equal to phi e. Okay, so we make use of that, and using this we end up with the following conclusion, namely that which implies gx belongs to 0 1 for almost all x with respect to phi. Okay, that is so this is the conclusion. So we have proved this result. Okay, now we do the next one. Now we just modify one of the identities in a way in which we can make use of it. Next step is so this is the third step. Okay, so next we prove that integral over x 1 minus g We completely get rid of that phi that is coming in. Okay. So how do we prove this? This is as follows. Integral over x f d lambda d phi is equal to integral over x f g d lambda plus integral over x that means d phi we change d phi we change in terms of d lambda and w d mu. So this is simply this. So this means now you can push these things. See, 1 minus g you can take. So integral over x one minus g f d lambda equal to integral over x f g w. So this is the remodification of this particular identity, the earlier identity, this one. Okay, right. So we have got things now in a sort of amenable form, right? Still we are some distance away from our h. Okay? So now our task is to find out particular h. So before that we do the following. We define two sets. A you define as definition strictly less than 1, and B you define as a set of all x belonging to x such that Gx equal to 1. Two type of sets we define. Okay. So this is exactly what is happening. This is A. You can easily see that A union B empty set. This is the breakup that you get for that. Okay, so we have ഹലോ ഞാൻ പിന്നെ വിളിക്കാം ഞാനൊരു ക്ലാസ്സിലാണ്. So A and B. So it is A union B is equal to X and A intersection B is empty. Right. Now we take E belonging to X. So this is something like this. This is E. So E can be split up into two portions, one like this and the other one like this. So you have take E. So E belonging to M. So you have E equal to E intersection A and E intersection A intersection E intersection That follows. Okay. Now we define lambda. So we define lambda A. Lambda A is defined as lambda A E defined as lambda E and equal to 0 So lambda E, this is true for E, for every E. Okay. Therefore, you get lambda A equal to, in fact, for X, this is equal to lambda zero. Okay. So this is the definition of lambda A. Similarly, we define lambda S E defined as lambda B intersection E and lambda S equal to 0. Okay, this is enough. Then we have to say all this. Therefore, what you get? So you get lambda A, lambda equal to lambda A plus lambda S. This is the breakup. It's lambda E equal to lambda A E plus lambda S E. So that is easily verified. For lambda A this is what you get. That's a breakup then. So you have now split lambda into two measures, sum of two measures, namely lambda A and lambda S. Right? So you see that this is the sum that you get for lambda equal to lambda A. Yes. Now what we have is we prove that so this is what we put F is equal to chi of chi of B in the relation then you see that on B G equal to 1. Okay. Therefore, what do we get? We get on B is equal to. So if you take on B, what happens? So integral over B one minus 1 this is equal to 0. That is, the left hand side is equal to 0. So the right hand side, on the right hand side, chi B G is equal to 1. Okay. And what we have is, therefore this is equal to integral over P W d mu equal to 0. Since W is positive, so we have from this, okay, we have integral over plus mu equal to 0. So what have we got? We have got that this is what we have proved, that lambda s zero imply lambda s concentrated on, okay. Therefore follows that mu b equal to 0 implies mu is concentrated on A. Okay. Mu b equal to 0, mu is concentrated on A. So lambda s is concentrated on B, mu is concentrated on A, therefore lambda is concentrated together. It follows that lambda A and mu are singular to one another. This is what we have. What next? Now once again we have 0, that is G is bounded. And this is less than 1. Therefore, replace F in this relation. That is 1 minus G F equal to G to the power n this is the crucial replacement. Okay, then you have substitute there. So if you substitute the integral over x 1 minus G 1 plus G plus to the power n, and this would be d lambda. Okay, this is equal to once again chi e this is what you get. What is the consequence of that? So the left hand side, if you take, what one gets is the following. So you just take the product of these two, then that will give you 1 minus G to the power n plus 1. D lambda. And the RHS is mu. So these two are equal, right? Now let n tend to infinity. on both sides. What happens to this? Because you know that G is 0 less than G okay, when G equal to 1, this will become 0. Otherwise, this will go to 0 as n tends to infinity. So this you get, this is equal to integral over E LHS gives lambda A. Okay, because G goes to in one side, on one side this goes to 0 as n tends to infinity. Therefore, the integral becomes simply this integral over E d lambda. Okay. So now G to the power therefore you can use monotone convergence theorem. The limit. Now let us look at the see here you have at every point of G equal to 1 on T and G okay. So that part P will go and you end up with this integral and finally you get this result. So this is lambda A. Therefore you get what you get would be you have this result. Okay, and G into 1 plus G to the power n plus 1 G to the power n so define H by as so let us define H then. Right, that again once again now look at this one G into 1 plus G to the power n times W. The limit of this to define as H. That is the definition of H. Just mark this out. This is well defined. You know the reason. The reason is this, that on A, G is strictly less than 1 and therefore this series actually converges and it converges to a function, a certain function G times that converges to a function and then with the multiplied by W you define that as your H. So the limit exists. then what you have is limits n tending to infinity integral over E you can interchange the integration and limiting process using the monotone convergence theorem. Okay, so you get this one. Limit and integration and integration. Limit and integration. And what one gets is the following. Lambda A use monotone convergence theorem. Justify. Because you see that this series actually pointwise converges to Hx, and this is what you get, and you can this limiting process can be taken inside this, so it will not change the result, taking the limit from outside or from this. So you get what you get on the other side, you have already obtained something. Therefore, what you get hence where H is given by this image. Now taking this is true for every which have integral over x d. Okay, and this is implies so we have proved this result, right? Now further what we have is this implies our mu e equal to 0 lambda A, that is absolutely continuous. Now this actually completes the proof of for positive. So for positive lambda we have proved the theorem. Essentially getting hold of G, and from G you estimate G, and from G you compute the H using this formula. This is the crucial constructing H. This is the H that we are going. And then we prove that lambda A is absolutely continuous with respect to mu, and lambda S is singular with respect to mu. And you see that from what we have proved earlier, it follows that these are uniquely different. Thus, lambda S and the consequence of this we have already lambda A is singular lambda. Okay, right. Lambda A is absolutely continuous with respect to mu, and lambda S is singular with respect to mu, implies lambda A is singular with respect to lambda S. So this gives the breakup for this we have proved for lambda real and positive. Now the next task is simple. For a complex measure, I think I have already explained it last time. So anyway, let me just recall it. Now, you see, it is quite simple. Suppose lambda is complex. Then I lambda 2, where lambda 1 and lambda 2 are real measures. Okay. Now what next? You take lambda I for both I equal to 1 and 2. You can write this as lambda I plus minus, where lambda I plus is equal to half of this is the total variation of lambda I plus lambda I and lambda I minus total variation of lambda I and lambda I. Okay, this is true for both, true for I equal to 1 to I equal to 1. So you have this breakup. Therefore, what you have? You have lambda is now written as plus this is the breakup that you get. Okay, both are non-negative. So both are non-negative. Therefore, what do you get? So you get no, sorry. Now work out for this one. Okay, so for lambda I plus, we will work out this. For lambda I plus, you have lambda I A minus. This is what you get. So lambda I A E is equal to integral over E H I plus minus H I minus dV. Therefore, H is equal to, where H is given by so lambda IAE is given by this one. Clear? This is for I equal to 1. So write H equal to this, then that gives that completes the proof of the theorem. Okay. So that actually completes the proof of the theorem. So first the strategy is first you prove for non-negative lambda and then take the complex lambda, write it as, take its real part and imaginary part separately. They are both real measures, and real measures you write as its positive part and negative part and write them as a sum. And then you see for the positive part, there are two parts for it, both are positive, and each positive part, so using these two, lambda I plus and lambda I minus, you can actually construct this lambda I A, etc. Okay, so lambda I is recovered using that, this, or in fact lambda is acquired. So you get this result finally, lambda A to HD. It's not lambda I, it is lambda A equal to integral E H d. That is just combining. It's just a matter of sitting down and writing out. So that completes the proof of the theorem. Now let me make some remarks. These remarks are important because to get an idea of where we stand, suppose the usual technique of analyzing a theorem is by trying to modify the conditions and see how far it stands. Okay, so that's the usual technique of analyzing a theorem. So we would have probably overloaded with conditions to get the result, at least in the process of simplifying them. So have we got the optimal conditions for the conclusions of the theorem to stand? This is the question that you are asking. For that, what you do? To start modifying the conclusions of the theorem. There are two things here, remarks. The first remark comes from the following fact. Suppose we assume both lambda and mu are positive, and sigma phi. Now, there is a small catch here. Okay, a real measure, lambda is positive, does not imply lambda is a complex. For instance, you take the for instance x you take as 0 infinity and lambda as the Lebesgue measure. Lebesgue measure. Lambda is sigma phi. But lambda x simple. Okay. Lambda, when lambda is a complex measure, you have less than infinity. It's a bounded measure. This is not a bounded, this is not so. Such a lambda is a bounded measure. It's not a bounded measure. Okay, that's a very important observation that you have to make. Okay, so whenever I say both lambda and mu are real, are positive and sigma finite, I am not assuming that they are bounded measures. Okay, they are, although they are sigma finite, and there is no problem about that. In this case, we cannot conclude that the representation theorem d mu has okay. I will give you an example. So this is the important part. In this case, we cannot conclude that. This is the important part. So we will give an example. Take x equal to 0 infinity. But I will make it. All that you can say is that h belongs to L1 locally it is. So you take both lambda and you take mu as the Lebesgue measure. This is a sigma finite measure. So lambda as twice mu, 2 times mu, 2 times mu. Then what you get? What you get? Equal to two dU. 2 dU. For h in this case identically equal to 2 on x. Okay. Now h does not belong to L2 what you call L2 mu. But h is locally L1 So what we have to do is, if we are assuming both lambda and mu are positive measures, then in general, unless you put some restrictions like boundedness or something, you cannot make the statement. You can all that you can say is that there exists an h. It's true that there exists an h. H can be taken as identically equal to 2 on this, but this h is no more L1 mu function. Okay, it's clear because you see that integral over 2 this is infinity, it's not L1 function, whereas locally this is an L1 function. So all that you will have to do is replace the condition or replace the conclusion by a statement that h is locally L1. Okay, rather than saying h is L1, you cannot anymore say h is L1. So that is one remark. A second remark is the following. These are also giving some insights into this theorem or limitations of the theorem. Second remark is this. Let us go try to forego sigma finiteness. Okay, so let us assume mu is the Lebesgue measure on 0 infinity. So lambda we take as the point measure. So let us take let us consider x equal to 1, 0, 1. So x you take as 0, 1. So here we have taken x equal to and Lebesgue measure, new Lebesgue measure. And lambda as the counting measure. Here this is of course sigma finite. So lambda mu is not sigma finite. Okay, right? So you cannot express it as the union of countable union of subsets, measurable subsets, with finite measure. So you cannot have something like this. This is not possible. This is not possible. This is not possible. Because it is the counting measure. Okay, because on the interval 0, 1, you have uncountably infinite many points. And you know every subset is measurable. Okay, right. No bound, no Lebesgue decomposition. That means you don't have such that there exists H. There does not exist H belonging to L1 lambda such that H d lambda. Now the example is this. Take a singleton X belonging to 0, 1. Then suppose this is true, then what happens? Integral over E H E lambda equal to, if E is singleton, Hx into lambda E, and lambda E is equal to suppose okay, and this is equal to, what happens to this? It's like singleton and D okay. Mu E, this is equal to 0 because it's a singleton. Okay, but integral over E H d lambda equal to Hx into lambda E. Therefore, either Hx is 0 or lambda E is 0. Okay, so lambda E is not equal to 0, which implies, since X is an arbitrary point, of interval 0, 1, we have identically equal to 0. H identically equal to 0. Then of course the relation won't hold. Okay. So this is a contradiction. Okay. Similarly, suppose H not equal to 0. Then we have lambda E equal to 0, which is again a contradiction. Because lambda E is okay, that is the reason. So we have, you see that the conditions that we have stated is an optimal condition. Okay, that's very nice, and thank you very much for being with me. And I hope you would take some pains to go through the proof of this theorem, because it's one of the central results that you have on complex measures. Thank you very much.